Hi. We are going to continue the discussion on corrosion and permeability. I think if you look at the program today, there are 3 talks on corrosion and permeability, which gives you some insight into what kind of the important discussion is that's going on right now with respect to BCSA cements and some things that we have to tackle here. I think we've spoken enough about the sort of theory, and by the way, I want to acknowledge my PhD student, Tayyab Adnan, who did most of this work. He's unfortunately unable to be here, so I'm presenting in his stead. I think we're all pretty familiar with the chloride problem. The chlorides go into the concrete, they depassivate the steel, they corrode the steel corrosion products are expansive. This is a problem. It's actually the biggest problem for concrete infrastructure globally, so we really need to tackle this, and we need to understand what's going on with the material before we can apply it at broad scale in steel reinforced concrete. So we're trying to tackle this problem, and really our approach is not necessarily to just measure the performance of the material, but to really understand if the tests we're performing are appropriate for the material. We have a suite of tests, and so we decided we're going to throw the kitchen sink at this problem. We had 4 BCSA mixtures. I think I've got a pointer here. Yeah, here we go. So our control is, there it is, 0.36 Portland cement. And then with the BCSA, we're at a 0.4, a 0.45, and a 0.55. Why are we using those water cement ratios? Well, our 0.55 with BCSA gets us 40 MPa, and so does our 0.36 with Portland cement. 0.4 gets us 70 MPa. So keep that in mind as we go through these results. Does it make sense to compare apples to apples or apples to oranges? Our cement that we're using is roughly 44% belite, almost 30% CSA, and 24% calcium sulfate. By the way, I have more slides than I have minutes to talk, so I'm going to move quickly so Lisa and Mehdi don't freak out at me over here. So we start with the old standby, the RCPT, right, C1202. And we cured these for 56 days, which my graduate student assures me is what the standard says. I think he might be right. I don't know. Anyway, performance is fantastic. We couldn't ask for anything better. Very low on all of these. All 3 BCSA mixtures and the Portland cement mixture get us exactly where we want to be in terms of chloride permeability. So that's fine, but that's just one test, and we have like a dozen of these that we can look at, so we've got to make sure they're all working for us. So we look at surface resistivity. We had something going on with our Portland cement mix here, so we're not going to worry about that one. We're going to go back and redo that testing. But we get pretty good performance here for the 0.4 and 0.45 with BCSA. We get very low according to the classification that we have here. As we go up to a 0.55, and remember that's comparable in compressive strength to our 0.36 Portland cement concrete mixture, we move up to low, but still perfectly acceptable from a chloride durability standpoint. We could use this in something like a bridge deck that's going to see a lot of salt, and we're going to have excellent performance from a durability perspective. Okay, so no problems here. Bulk resistivity. All right, so we take our concrete cylinder, we send some, wavy electrical signals through it, AC impedance, really. And one of the things about this test is it has to be soaked in, I believe this one. So one of the tests is soaked in saturated lime water. The other is soaked in a simulated pore solution. I believe this one's soaked in a simulated pore solution, but that's a simulated Portland cement pore solution, which, as Lisa spoke about earlier, is very different than a simulated BCSA cement pore solution. And so we get some kind of weird results. We get moderate permeability for a 0.4 with BCSA. We get moderate permeability for a 0.45. We get high permeability for a 0.55. And these, by the way, are done at 28 days. So these results so far do not agree at all with what we're seeing from the other tests. This tells us something about what we have to do here, and particularly what we're paying attention to is what the specimen is soaked in. So should we be soaking it in something that resembles a Portland cement pore solution or something that resembles a BCSA cement pore solution? More on that later. So then we go into some of our more heavy-duty methods, right? These are a little more difficult to perform, but they maybe give us a little bit better idea of what's going on, maybe a little more indicative of what's happening from a transport perspective. So we start with the NT492. This is a pretty popular test, more popular, I'd say, in Europe than it is in the US, but, you know, we're catching on over here. We're a little slow on this side of the pond. So we get about 10 times 10 to the minus 12 migration coefficient for the Portland cement mix, much lower than that for a BCSA with 0.4. Remember, that's a much higher compressive strength concrete. So are we comparing 40 MPa versus 40 MPa? Are we comparing, you know, 0.36 versus 0.4 water cement ratio? We've really got to decide what the approach is going to be there. As we increase our water cement ratio, we see an increase in the migration coefficient, which should correlate with the actual diffusion coefficient, not exactly, but it should be pretty close. We move up to something like 10 times 10 to the minus 12 with a 0.45 and almost 20 times 10 to the minus 12 with a 0.55. But again, these classifications here are based on what we see with Portland cement, and so we don't really know if that's a good classification. We don't know if those rules should be applied to a different cement type, because we know that the chloride permeability problem really depends on several things, right? So it's not just about the pore connectivity and things like that. It's also about the pore solution. So moving on, the other thing we need to talk about with NT492 is how we compute the migration coefficient. So the migration coefficient depends on this parameter E, and also this parameter alpha, all right? And in this equation, we have something called C sub D. So the way we determine the migration coefficient is we split this sample in half in a split tension configuration. We stain it with silver nitrate, and we measure the depth of chloride penetration based on where that color change boundary is. And we know that for Portland cement type materials, C sub D is 0.07 normality. That's when we think the silver nitrate is going to change color in terms of chloride concentration. We have no idea what that number is for BCSA, and I think there's a lot of evidence to say that that number will be different, and we need to do some fundamental studies here to determine if we can use 0.07 or if we can use something else or should use something else. So this is some work that needs to be done in order to modify the test standards here to be applied to a different material. And by the way, this type of study has been done for a lot of other alternative cement systems, such as alkali activated materials. There's a lot of modifications to the standards that we had to look at for alkali activated materials, so there's a lot of reason to say that we should do the same for CSA and BCSA class materials. So we move on to the bulk diffusion test. We also did some ponding tests, but ASTM revoked the ponding standard years ago for a lot of good reasons, so I'm not going to show those data here. But we did the bulk diffusion, so we took the sample, we epoxy coated it on all but one face, and we stuck it in the solution for, I believe this was 35 days, I think is what the standard recommends as the minimum exposure period. And then we did some profile grinding, and we got some pretty surprising results here, actually like an order of magnitude higher diffusion coefficients in the BCSA than we had for the Portland cement. And this is where we have to step back and say, well, okay, what's going to happen if we actually match that Portland cement water cement ratio? What's going to happen if we change curing time? So these were cured for 28 days. Now, a lot of the hydration in BCSA happens very early, but we get that later age B-light hydration that's going to really refine the microstructure. It's not only going to add strength, but it is going to refine and densify the microstructure. So should we consider that in our testing period, or should we continue with a 28-day testing period? So here's a comparison of results, and there's a lot up there, but what I want to highlight is it's really a mixed bag. So depending on the test you have chosen, you could find that your cement and your concrete mixture is fantastic or horrible, all right? And in a perfect world, we should have perfect agreement among all these tests. It's worth noting we don't even have good agreement in these tests for Portland cement concrete, and that's well known in the field, all right? So we have some imperfect test methods, and the imperfections of those test methods, I think, are highlighted when we apply them to BCSA. What does this mean for corrosion? So Eric's going to yell at me too. We said the best thing we can do here is apply ASTM G109. So we went ahead and we cast these specimens. The graduate student came up with a nice little system where we cast it upside down with a void in it, so it creates its own moat, which is kind of cool. What we're doing is we're taking the corrosion current, we're integrating it with time, and what we want to see is this should be under 150 coulombs. And so down here, you can barely see it, that's our Portland cement concrete mixture. And it's doing just fine. But right from the very first cycle, we start to see indications of corrosion happening in the BCSA concrete. By the way, the G109 standard says cure it for 14 days, moist cured, dry it for 14 days, and then load it up with chloride solution. We said, well, that can't possibly be happening. So we autopsied the specimen and we found brown rust. We found indications of corrosion. This is after one cycle of chloride exposure. So this tells us that something's going on here, right? That RCPT number tells us that it should never corrode because the chlorides should never get to the bars in the first place. But we're seeing something different. And by the way, you know, when you dry that sample out for 14 days, it becomes a sponge and it's very thirsty and it's going to do all those processes that just suck that chloride solution down into the concrete. So it's a pretty rough test method. We also did the same with the half cell potential. When we get below minus 350 here, we say that we're likely to have corrosion. It's hard to tell for sure until you autopsy the specimen, but that's the mark where we say we have 90% probability that corrosion's happening. And again, our Portland cement concrete's doing okay, but regardless of the water cement ratio, we see early indications of corrosion. So what does this mean? And what lessons can we learn from this? And what can we do to better assess the corrosion performance of BCSA concrete? Because we know that there's a lot of BCSA concrete out there in the field, and none of it's corroded. None of it has corrosion problems. I have not seen, in all my research, I've not seen one indication that a field application of BCSA concrete has had a corrosion problem. So clearly, there's something going on here. What I want to look at is what happens in the hydration of BCSA, and we've seen a lot of people looking at GEMS today, the Gibbs Energy Minimization software, and I'll have you note that we're just starting to play around with this. There's a reason I'm showing you this, but the composition that we start with over here does not exactly match the composition of the cement we're using. But I want to point out what happens when we have the B-light, right? So of course the calcium sulfate and the CSA are going to react early. They're going to form our ettringite. They're going to form our aluminum hydroxide. The B-light, in the presence of aluminum hydroxide, is going to hydrate to form stratlingite. Stratlingite, one of the things that it does is carries with it just a whole mess of hydroxide ions. So when we talk about passivating the steel, which we think is the issue, that's why we see early corrosion. Of course, the steel is not passivated. So when is the steel going to passivate? And the steel is only going to passivate when the pH is elevated to a sufficient degree to passivate it, right? We need a pH of something like 12 to passivate the steel. And this is the only thing, this is the only hydrate that's going to carry with it some hydroxide ions to give us that passivation potential. And so we said, all right, I think we're onto something here. With that later age hydration of B-light is going to give us the alkalinity we need to passivate the steel. So maybe we're just testing too early. We said, let's have a look at the pH. What's happening with the pH? And we applied two very basic methods here. We'll apply some more advanced methods later. But we looked at a dilute slurry because I wanted to know what was happening very early in the process. Yep, I got like one slide. And so this is a water cement ratio of 3, super high, so that we can get the formation of hydrates, but it won't set up, and we can keep our pH probe in there without losing it. And we see that we end up with an early age, we get our initial dissolution, and we get a pH of around 12.25. That's probably overestimated because, with that much water in there, we can really get everything into solution. And we use ex situ leaching, so we make some cubes at 0.5, we do solvent exchange at different periods, we grind them up, we eviscerate them, and we dissolve in basically 1 by 1 volume of deionized water. we measure the pH, and this is the behavior we see. Now, the real pH is probably somewhere in between these, but this elevation in later age pH exactly corresponds with the time period at which the stratonite is forming. And so if we are testing our corrosion test right here, but our pH is elevating all the way out here, then we're not giving the bars sufficient time to passivate, and we should basically extend the testing period for our corrosion test. What we're throwing at the material is really not a fair characterization. So we've got a few tests, or a few remaining questions. We want to basically figure out, does this later age hydration of belite and the elevation of the pH translate to better corrosion resistance? Right now, we think probably. I'll have those data in about 3 months. Do the chloride penetrability results correlate with better later age corrosion performance? So do those RCPT numbers correlate better with later age G109 results than they do with early age? I think probably, but again, give me a couple months for results. And finally, when we talk about the pore solution, we really need to bring in the formation factor, because that combines the pore structure and the pore solution in a way that the existing tests can't. And we're going to verify our results from our simplified pH analysis with some direct pore solution expression and try to understand where that pH is exactly. And our pore press should be fixed by the time I get home. So thank you for your attention. I'm not sure if we have time for questions. I'll leave that up to Mehdi.